Today, we're going to continue our exploration of normal probability distributions by taking a look at some real applications of normal distributions. This is going to allow us to get away from just that standard normal distribution that we talked about last time. So, with the real applications, it turns out that oftentimes the mean is not 0, or the standard deviation is not 1, and very often both of those things are true. So we're going to look at how we can standardize any normal distribution so that we can use all the same methods that we learned last time with the standard normal distribution to solve problems related to those probabilities. So our conversion formula should look very familiar. It's our z-score formula. So we have z equals x minus mu divided by sigma. So x minus our mean divided by our standard deviation. This formula allows us to standardize any normal distribution so that x values can be transformed into z-scores, and we can use our table then to help us find these probabilities. So for those of you who loved graph transformations at some point in life, all the z-score formula is doing is it's shifting the mean from whatever it is to 0 by subtracting it. And then by dividing by the standard deviation, we're shrinking or stretching our graph so that our new standard deviation will be 1. So that's what's going on. This is the shift, and let's take a look at how we do this. So first things first, it's really helpful to look at a graph. So sketching what a normal curve looks like, shading the region that we want related to whatever x value. So if we want to know the probability that's greater than or less than or whatever, shading that area that corresponds to that probability is a great idea. And then what we're going to do is underneath of our horizontal axis where we have our x labels with the mean and our x value, we're going to make a second axis that's a z-axis where the mean will be 0 and the x value that we're interested in, whatever that boundary value is going to be transformed into a z-score to be standardized, and we'll label that on our z-axis. All right, so let's take a look at an example. What proportion of men are taller than 72-inch height requirement for shower heads? All right, some of you may have had this issue before where the shower head is not actually taller than you. So how many men have that problem? So heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. So we want to find the percentage of men who are taller than that shower head 72-inch height. So the first thing we're going to do is we're going to sketch a graph of a normal distribution, and we'll label the mean of 68.6 inches. And we'll keep in mind that our standard deviation is 2.8 inches. And then we're going to label our x value that we're interested in of 72 inches. And since we're interested in how many men are taller than this, we're interested in greater than 72 inches or that area underneath the curve to the right of 72 inches. So we've shaded that region in. Then what we're going to do is we're going to convert our shower head height of 72 inches to a z-score. So we'll use our z-score formula, and we get 1.21 when we round to 2 decimal places. And so we're going to add that axis underneath of our x-axis. We'll have our z-scale, our z-score axis, where the mean is labeled as z equals 0, and the value for 72 inches is 1.21, like we found. Now, we're either going to use technology or a table to find that probability. So we're going to use the same techniques that we used last time. Just to note, when we're finding z-scores, we're rounding for the z-score. And in doing so, what we do is we make our answer a little bit less accurate than it would be if we used technology that didn't require us to transform things to z-scores. Don't worry about that difference, all right? If we had used technology, we would get 0.1123, and if we used the table, we'd get 0.1131. Ultimately, that difference is not a big deal, and we're going to be dealing with the table for the most part. So, using table A2, what we're going to do is we'll look for our z-score of 1.21, and it's going to give us a cumulative area to the left of that value of 0.8869. So again, to find the area to the right, we'll be taking 1 minus that probability, so we'll take 1 minus 0.8869 and get a value of 0.1131. So interpreting that, again, this is the one that the technology would give you if we didn't translate to z-scores, but our table would give us the 0.1131. Either way, they're close to the same. So the proportion of men taller than 72 inches is 0.1123 or 0.1131, which is about 11.23 or 11.31%, which is about 11% of men who might find showers a little bit uncomfortable with the height of the shower head. All right, so just like we had before with our standard normal distribution, we also sometimes in the real world know areas, and we want to find the x values that go with them. So again, looking at graphs can be incredibly helpful. So sketching a graph is always a great idea, and labeling that area that you're looking at and whether you know it's greater than or less than is always a good idea. Again, be careful, don't confuse z-scores and areas. Z-scores are those labels on the horizontal axis. Areas are the area underneath of the graph. And so we'll use it table A2 to get our z-scores, or to get our z-score by using that area. The areas in the body of the table, the z-scores are the labels on the columns and the rows. So we will do that. And one quick thing, again, remember table A2 is going to give us the area to the left always, so corresponding area to the right, keep in mind which one you're dealing with and use the techniques that we used last time for that. And make sure that you're translating the words that you're seeing into the correct side also. So when we're asking about separating out the top 10%, then we're looking for 10% to the right. If we're looking at separating out the bottom 10%, we're looking at 10% to the left. And a couple of other tips, ways to know if you've made a mistake along the way. So a z-score must be negative when it's located in the left half of the normal distribution. So if you end up with a z-score that's in the left half and it's not negative, something went wrong somewhere. And also areas underneath of that graph, which correspond to probabilities, they have to be between 0 and 1, and they should never be negative. So another troubleshooting tip, or at least way to know that trouble is in the air. All right, so procedure for finding values from known areas or probabilities. So this is going to look really similar to what it was last time, except where we have this added complexity of we have real x values instead of just straight up z-scores to deal with. So we want to be able to identify the x value, and we're going to go through the intermediate step of identifying the z-score. So step 1, you're going to sketch the graph to help you out, and you're going to identify where the x value should be about based on the area that you're looking for. And then we're going to go through the steps that we went through last time to identify the z-score that goes with that area. And then we're going to use that z-score formula that we had. If we solve it for x, we get x equals the mean plus the z-score times the standard deviation. So since we know the mean and the standard deviation, we're able to use the z-score that we found, multiply it times the standard deviation, and then add the mean, and that will give us the x value that goes where we marked it on the sketch. And then, of course, we will always want to do that gut check of, does it make sense with the context of the problem? Does that x value make sense? And if it does, then we're golden. So let's take a look at an example here. So designing an aircraft cockpit. When designing equipment, one common criterion is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirements for U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. So assume that heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. So in addition to the maximum allowable height, they also want to know, should there be a minimum height and why? That's a real world thought to have. So let's start off with the math. Let's find that 95th percentile. All right. So here we have a picture of a normal distribution. We know the mean is 63.7, and we know the area we're looking for is the area to the left, and we want it to be 0.95. So then we sketch where is the x value about, and we go looking for it. So we can use technology to help us out, but let's take a look at using a table A2. So if we're using table A2, we're going to search in the body of the table for 0.95. And when we find it, we're going to identify the z-score that goes with it. So when we identify the z-score that goes with it, we'll get a z-value of 1.645. So 1.645 is one more place than we normally have in our z-scores. And the reason that we're able to do that is because there's a special note that actually says that 0.95 corresponds to 1.645. Right? Because 0.95 does not actually appear in the body of the table. We instead have only values of 0.945, or 9495, sorry, and 9505. So we're going to use that footnote. We have z equals 1.645. And then once we have that, we can plug that in for z to our z-score formula, plug in the mean, plug in the standard deviation, and then we're going to solve for x. Solving for x, we get 68.4705. So what this means is 68.5 inches is greater than the mean, so it seems reasonable, and it means that 68.5 would have to be the height requirement. So you'd have to have a height less than 68.5 inches, and that would allow 95% of women to be eligible as U.S. Air Force pilots. So the other question was, should there be a minimum height requirement so that the pilot, and the answer is yes. Similarly to, we want people to fit into a cockpit, we also want them to be able to reach controls. So if we wanted 95% of women to be eligible, we probably would actually choose a middle 95% rather than just the shortest 95% as we've done here.